Yeah, go.
Right, hopefully we're back again. We were talking about solenoid, which is a long straight coil of wire that's been coiled around to look like a spring. I was saying that the magnetic field generated by this is similar to the magnetic field of a bar magnet. And in fact, if you place a magnetic material, and I said there's only 4 you need to worry about: iron, steel, which is an alloy of iron, nickel and cobalt. They're the only 4 magnetic materials. If you place one of those inside this solenoid, you actually create an electromagnet. An electromagnet it increases the power or the strength of this magnet that the solenoid is creating. So that's how they would create an electromagnet. An electromagnet is one that you can turn off and on, because if a piece of iron was in here, it wouldn't be magnetic until you turned on the current, and when you switched on the current, it would be a strong magnet, and if you turned off the current, the magnet would then die. It would lose its magneticity, because it's only iron is a temporary magnet. A permanent magnet is something that's magnetic at all times. A temporary magnet is something that only becomes a magnet when it's placed inside a magnetic field, such as in the middle of a coiled piece of wire. So this is to make solenoid. Now there is this way of telling which way is your north and which way is your south of the solenoid, and the way you do that is if you look down the end of the solenoid. So if this was our solenoid coiled with a bit of wire and we were to look down it like that, if the current was passing around in this direction, this would be north, because it makes an N. If you drew this little line here, and join them up, that's an N. So that's the north end of our solenoid. So if we were to look down from this end, this is the north end of the solenoid. Similarly, if the current was flowing in the opposite direction, so round here, like it would be here, going around in that direction, that makes an S, because we make this little S shape here. So you have a north and south side to your solenoid as well, which you can identify by looking down the solenoid. Magnetic flux density, that's just a sort of posh word for the field strength. Now I said the strongest part of a bar magnet is at the poles, because the field lines are closest together, and that's similar in this instance. The flux, or the magnetic flux density of these 2 magnets combined is stronger than this, because there are more field lines between them. And magnetic flux density, why we talk about it, is because we need it for a calculation. It's a new one. It's measured in Tesla. You might have heard of the name Tesla before, and they've given that as the units for magnetic flux density, or T is just the symbol they would use for the units. The symbol they use for flux density is actually, funnily enough, a B, and this is another equation that you need to use, but you are given this equation on your equation sheet. But FBIL is the equation. Force is equal to magnetic flux density times the current times the length of the wire that's in that magnetic field. So F, force, is equal to B, the magnetic flux density, times I, the current, times the length of the wire. The crucial thing about this, we said this was measured in Tesla. Forces are always measured in newtons. But I do really think there'll be an element in this exam of them giving you units, but in the incorrect version. So instead of amps for current, they may give you milliamps. Instead of meters, which length should be measured in science, they'll give you it in centimeters, or possibly even millimeters. So, for example, if we're given something in milliamps, so if we're given 1 milliamp, we need to convert it. Now the way you convert a milliamp, milli is 1,000th of a full one, so you actually do 1 divided by 1,000 equals 0.001 amps. The temptation of students, I think, quite often is when they get a number like 1 milliamp is to times it by a number. Now that you can already tell is wrong, because a milliamp is a tiny measurement. If you were to times that by 1,000, you'd get 1,000 amps. You're essentially saying that 1 milliamp is 1,000 amps. Well, that has to be incorrect, because a milliamp is a tiny measurement. So it has to get smaller, that number. We should end up with a small number, quite often below like 0, or below like 0 point something is what we need. So for milliamps, you divide by 1,000 to get it. Similarly, we need the length in metres. The length of the wire should be measured in metres. Now, if you're thinking about that scenario that I had earlier on, if I just go back to it ever so quickly, about this wire that's in a magnetic field, you're probably not going to be able to fit metres of wire in there unless you coil it, which is what they do, a clever trick which we'll come to. But in reality, the length will be given to you in most probably centimetres, but possibly millimetres could be given as well. So if we did centimetres, if we had, say, and I'm just going to pull a number out, 10 centimetres, okay, we want it in metres because the length should be measured in metres. So 10 centimetres, centi means 100, so we need to do 10 divided by 100. Okay, that tells us it's 0.1 metre. Okay. You have a calculator in exam. Don't worry about trying to do this in your head. Just type it into a calculator. Just remember that it's divided by 100 and you can get it. Similarly, if you were given a number of 10 millimetres, okay, you could convert it to metres again. But for millimetres, milli, just like here in milliamps, means divide by 1,000. So if we divide by 1,000, we're going to get 0.01 metres would be our distance. Okay, but again, you all have a calculator, so just hit it into that, get the number. Sometimes I see students when I do assessments doing the mental maths on the paper, they're trying to write it all out. You have a calculator in the science exam, there are no non-calculator elements like in maths, so use it. It's a tool there to improve how you do these calculations. So they can ask you, how could you increase the force that that wire feels? So in the motor effect, you want to increase the force to make it a stronger force, to make more movement or more motion. So it's all about increasing these different things, because if the force is equal to the flux density, which is the strength of the magnet, times the current, times the length, if you increase any one of these, you're going to increase the force. So if we increase the flux density, which means we put it in a stronger magnet, so we have a stronger magnet, that will increase the force. If we increase the current that's flowing, if you turn up the current, then again, you are going to have a stronger force. And similarly, if you increase the length of the wire that's in between that magnet, you're going to increase the force. The length of the wire is a tricky one to increase, so what they will do is, and this is where coils come in again, they actually coil the wire around before taking it out of the magnet. So it'll go in between the two magnets, coil it round and then come out, because the coil increases the length, because if it was just straight there would only be that much in between the magnets, whereas if it's coiled, you stretch out the coil, you've got a long distance in between the magnetic field. So to increase the force, you increase either the strength of the magnet, the current flowing, or the length of the wire in between the magnet itself. Now why is that relevant? What's that important for? It's important for electric motors. Now electric motors really are the most tricky thing within P2. It will be unfortunate if it cuts out during this bit, because this bit is hard to follow anyway, I always think. So if it cuts out, I'll go through it again from the start. I know we may go a little over at this point because of the interruptions, but it's worth me spending a little bit of time on this. We are very close to the end. And it's worth me just getting this right, because it's something that even scientists, I mean half the science department have to think carefully about it, and we're super intelligent people because we're science teachers, and as you know we're the most intelligent in the school, so we have to think carefully about it. So it's really difficult to actually get this concept, so we'll go through it and we'll go through it carefully. So an electric motor, the way it works, electric motors work by having anything with an electric motor in. So start with that actually. So think about things with electric motors in. We're talking about like electric drills, like anything like that, anything that sort of rotates, an electric fan, those things will have an electric motor, an electric toothbrush would have one in it. All of these objects have an electric motor that spins around and causes a movement or a motion. And in it they have to have a magnet and some sort of electricity that passes through that magnet in between the field. So what we have here is we have a simple battery powered electric motor. Battery power here, so the battery is attached and electricity is flowing in terms of the current flowing around this circuit. Now this thing, this important thing, and if you can't remember anything about it, remember this, it's called a split ring commutator, and I always struggle to say that, but if you've got the slides you can read it off there, commutator. Commutator, yeah, I'll try again, I always have trouble with pronunciation, you know that from the previous videos. But anyway, that is a crucial bit, because if you just even mention that when talking about electric motors, that can be enough to score you a mark, because it's a crucial bit of it. And I'm going to tell you how it works. When the electric current goes into the commutator, it goes through this coil. This is a coil of wire that's been coiled up. And it goes to the other side. And then it goes back round so it can get to the battery. Because as we know from P1, electricity has to flow all the way round from one side of the battery to the other for it to actually flow. Any break in that connection, it will stop flowing. So, it can flow nicely through one side, and you can see the arrow going back into the board. This is supposed to be going backwards, so my second finger would be there, going back into the board. And similarly, it's coming out of the board here. Okay? So when we turn this on, we actually generate a motion, because we've got electric current inside a magnetic field. And that's going to cause the movement, or the motion to happen. When the motion starts, one side of the coil is going to move up and one side is going to move down. I have a little coil here, I don't know if you'll be able to see it very well on the camera, but this is what the coil looks like. This is one piece of wire, but in reality they would coil lots round and then bring it out. So essentially one side is going to move up and one side is going to move down. Now the effect of that is going to be a rotation. If that's to rotate when the force is produced up and the other force is produced down, eventually it's going to flip over and it's going to be the other side. Now if that's to occur, if my hands were providing the electric current, the current is still going the same direction in either side, which actually causes the force to be reversed, and it just keeps flipping back and forth. So that motor cannot spin, it just goes back and forth. So this being a fixed connection, it will have a problem. The force this side, I'm just going to say, is up, and the force this side is down, which causes it to do that. When it gets over here, the force on this side is still up, and this side is still down. So it causes it to go back, up, down, down. It just keeps flipping. So that's a problem for electric motor, because electric motor, as you can imagine, we want to spin around, keep spinning. So that's what the commutator does. It actually has a split in the middle, hence split ring. So when it gets to the upwards position, it starts like that, when it gets to this position directly up, it actually reaches a break. There is no more connection at that point when it gets to this coil being vertical. And that actually allows the momentum to just keep going and turn it all the way round to finish off.
There you go.
Right, hopefully we're back again. So, instead of go through like all of electric motors again, so talking about it, we've got the current going in here. I know we didn't lose it right at the start. We've got current flowing round, the split ring commutator, which I always struggle to say.
Right, try again.
Right, back again. See if I can beat Mr. Pritchard's record of going on and off 15 times, I think. So, going back. Again, going through this little section of the commutator, you're going to know that word, like definitely in your exam, you'll get 1 mark for that, because I've said it like 15 times. So current flows through, goes in the commutator, goes around, comes back. As it causes that motion, it goes to this point, and the split actually causes the connection to break, and momentum keeps it travelling over to the other side. Once it gets to the other side, the current has actually been reversed. And what I think shows it nicely is this animation here. Now, if you download it and you're looking at this electronically on a PC, I don't know if it'll work if you're just taking it and you're looking at it at a phone, the animation. But what it actually shows is, follow this orange side. So the orange side is there, it goes there, and now it's over here. And then it goes here, it's over the other side. It goes here, and it's over the other side. What that's showing is that the current going through that side of the wire is actually reversing, because rather than me flipping it back and forth, because my hands can't cross, I get caught up. So well, it might be back up and going again. Yeah. So as I said, the commutator reverses the current that's flowing through the coil and hence keeps the direction of the motion going all the way round, and just keeps going around. Just like I'm swapping my hands here on either side of the coil, it keeps switching the direction of current and hence keeps the motion. Right, might be streaming live again. Okay. So, what it is now, we've had lots of disruptions, and at this point, and we'll see how long it goes on for, anyone who's slogged it out to this point in the video, I'll offer a little prize. You time how long it takes me before I cut out again, and if you come in and tell me tomorrow, then I'll give you a little prize for that. How about that? Hopefully we'll make it to the end of the video. So, when the current is reversed, it keeps the direction, keeps it moving around, and if it keeps going around, it will keep the electric motor spinning in only one direction. Now literally the last thing I've got to say, and you'll be thankful because it stops all the cutting out, is that's if there's a DC supply to the electric motor, because DC supplies only flow in one direction. So you have to keep reversing it by the split ring commutator. With an AC current, the AC current's a bit different. Okay, you need it to be able to move. Now in an AC electric motor, if it was a fixed wire, AC, remember, the current reverses direction naturally. That's what AC means. Direct means it just keeps going round in one direction. AC means it flips from one way to another. That works for electric motor because we want the current to flip. So in fact, you don't need to have that commutator to actually flip it around. It's doing it anyway. So it will just keep moving in one direction all the way around and just keep spinning. The difficulty is if you just attach wires to either end of the coil, they will get caught up in each other. They'll get twisted, and the motor will get caught in itself and will stop working. So with an AC current, you just need like slipping contacts, which are just like brushes, which are rings that touch either side of this and allow it to move but still stay in contact. So it's like a ring that it just rubs against, that goes all the way round and allows it to stay in contact while allowing it to move at the same time. Because every time the coil flips 1/2 turn, the current flips naturally in the same time, which keeps the coil moving in the same direction. Okay. So we've reached the end, we've got through it just about, okay, with 1 or 2 interruptions and 1 or 2 little slip-ups, but we've got there. I don't know what the problem was today. We've been fine all the way through all the others. It seemed to be having a bad moment, and it's caused us some issues. For those of you who managed to make it through to the end of the video, pineapple is the code word you need to tell me tomorrow for a chocolate bar, and well done for making it this far in. We'll see who gives me that code word and who actually makes it to the end. I might not bring chocolate bars if too many people win, but anyway, thank you very much for watching. Good luck with your exam tomorrow. It is the last one you will do before sort of finishing this exam period. I know it's been hard for you, and well done for slogging it out and making it to the end. And it will be really fitting if I'm halfway through a sentence and the feed just cuts out before we've actually finished. But it's not now, it's going to work perfectly, of course. So I'll be in tomorrow, the exam's in the morning, and just think, it's the last one. So I know we're already quite late at night, try to put in some effort, do that revision, come in with some questions, please do, things you want to ask about. If it's something in the video you missed out on because it cut out at some point, I really would like to see a large number of us in tomorrow morning, like up to like, well, let's say there's 250 of you in the year, like 100 of you coming in asking questions because you watched the video and you missed something, would be brilliant and show we're really keen and want to do well in this last one. So other than that, I'll see you tomorrow morning. Best of luck with your exams and well done for getting this far.